Right, hi everyone. Welcome to another introduction to astronomy. Okay, so just imagine that this was you sitting out there, lovely dark sky like this, admiring the beautiful night sky. And you see all these beautiful stars up there. And a few people, so I'll start right up front, because a few people have said, hey, what are stars? You know, it's introduction to astronomy. I've come here to learn. What are stars? And so I'll explain that a little bit. So essentially, what stars are huge, big spherical balls of an extremely hot gas known as plasma. And you're probably all familiar with your high school, what you learned at high school. If you've got for an atom, it consists of a nice central nucleus that's positively charged, and you've got all these loads of electrons negatively charged that are buzzing around it. But the temperatures in stars are so hot that the negative electrons cannot be held onto the positive charged neutrons. So they're just all flying amok. Electrons and positively charged nuclei just running amok, all mixed in together. And that's called plasma because it's extremely hot. So you might then say to yourself, well, if it's so damn hot up there, what holds the star together? And the answer to that is gravity. Stars are really massive, lots of matter. So that generates lots of gravity, and the gravitational inward force just raises the temperature and the pressures at the very core of the star to huge millions of degrees, whereby these nuclei that are roaming around that are positively charged, naturally they're going to repel one another, but the pressures and the temperatures are so intense, they just get smashed together. And you get what we call nuclear fusion, the fusion of two small nuclei, commonly hydrogen, to form the larger helium. A little bit of mass is lost in that process, which is released as energy, as light and heat pours outward. And that outward force from that nuclear fusion energy equals exactly the inward gravitational force, and you get a stable star. That state is called hydrostatic equilibrium. And it's a nice stable state that stars spend most of their lives in. So that's what stars are, because people often ask that question. Tell me, what exactly are stars are? So next time when someone's like, you're sitting out here in the field like that looking up and someone says, oh, those beautiful stars. You say, no, you're looking at thermonuclear reactions in the sky. That's what you're looking at there. So now, and stars, as you can see there when you're looking up at the sky, one of the things you notice is that stars come in a variety of sizes, colours, brightness. Obviously not with your eyes, but you're probably aware you can measure their temperatures, which we'll talk about later. So a wide variety. And I've just, for example, just sizes and so on. Look, here's our sun here. You can't even see it on this diagram. Look at the size of Betelgeuse and Antares in the sky, how huge they are. So stars, they vary in temperature, anything from 2,500 up to 50,000 degrees. Imagine that. You know, that's the range of temperatures you're looking at. There's loads of names. We'll talk about some of these during the talk. And I've just put a slide here to show you where those two big guys are in the sky. So here's the constellation of Orion for us Southern Hemisphere people. Down here, it's in our summer, over December, January and surrounding months. And Betelgeuse is down here. And in our nice current winter skies, there is Scorpius there, the constellation Scorpius, the scorpion. You see there's its tail, and there's Antares. So these guys are red supergiants, which we'll talk about. But look how big they get. So we're going to be talking about those and how they got there and so on tonight. Now, supposing you thought, well, all these different sizes and colours and brightness, these properties of stars, what say we tried to make some sense out of it all and put them into a graph maybe, a plot sort of graph. And if you just got a random quantity, they've called it here, quantity y for the y-axis and quantity x, just random things, that's probably what you get. Do you make any sense out of that? No, that's just a scatter chart. So, but what say, and that's what two famous astronomers said to themselves, what say we plotted the luminosity or brightness, we're going to be talking all about this shortly, but the luminosity or brightness, we did a nice logarithmic scale here on the y-axis, and along the x-axis we put the temperature of stars, and we'll actually start at the hot here, and then we'll go down to the cold. That seems counterintuitive, doesn't it? Normally you start at the low levels here, but they did it the other way around, and suddenly, look what you've got. They all fit into organized groups, the stars. That's telling us something. And what that is, it's called the Hertzsprung-Russell Diagram. Think of it as the periodic table as to chemistry. The Hertzsprung-Russell diagram is to astronomy, is one of the single most important tools that astronomers use to look at stars, and we're going to learn about information. So tonight's talk is about, it's the Hertzsprung-Russell diagram, stars and stellar evolution explained, because that's what the diagram does. Let's delve deeper. So this is what you're going to learn about tonight. We'll talk about, briefly introduce you to the two astronomers, Hertzsprung and Russell, it's named after, and then we'll talk about the diagram. We'll then talk about main sequence stars, red giants and red supergiants, some stellar remnants, and then we'll just talk about some gaps and variations of the Hertzsprung-Russell diagram, and then we'll wrap up with a summary and conclusion, and then we can have some questions. Okay, so it's these two guys here. A Danish astronomer, Einar Hertzsprung, in 1911, he was starting to play around with this, playing around with figures. What's how we do logarithmic or different scales and stuff. And he cottoned onto this. And then 2 years later, American astronomer Henry Russell, in 1913, he realized totally independently, these two guys, they'd worked this out, that this was the way to think of stars. And it was in 1914 that a paper was published, I think by Russell, and then the International Astronomical Union got together and decided, let's give both these guys the credit to this. This is such a hugely powerful tool that these guys have come up with. And that's it there. So it's a plot on the y-axis there. You've got luminosity. Luminosity means the power output, how much grunt or power a star is putting out. And you could quite happily swap that with brightness. And sometimes stars, you'll have brightness or their what's called magnitude, which we'll come to shortly. Sometimes you'll have that on the y-axis as well. But you will notice here it's logarithmically. And I'll show you in a minute how luminosity can be expressed in two forms, the amount of wattage that a star produces, but commonly you do it as a ratio, proportion of related to our sun. Our sun's called one, obviously, as one luminosity. So here's one. So our sun, if you go across here, we've actually labelled the sun there as well. So luminosity, one is our sun, and then, but look at how the huge range. Suddenly you've got up to 100. That's 10,000, that's up to 1 million times the brightness or the luminosity, the power output of our sun. So one of the reasons they obviously went, and you're going to dimness right down to 10,000 times dimmer than our sun, they had to go logarithmically, otherwise you would have never fitted it all in. But that immediately highlights to you the huge range. We think our sun is bright. Whoa, sun's in my eyes. No, our sun's a baby compared with the brightness, up to 1 million times bright some stars are. Then on the x-axis, they've put temperature here, and they've also put in colours, because colours often match up with temperatures. And you go, really? Yeah. A flame, when you're on your gas stove or something like that, a very cool one is red. You start cranking up, it starts turning white. You crank it up a bit more, and the flame turns blue. Put a steel rod in the fire, does the same thing. It starts going red, and as it warms up, and then it glows white, and if you get it hot enough, you'll go blue. So colours do relate to temperature, and these guys were well onto this as well. So they've got their temperature here. That's logarithmic as well, and as I mentioned, it was counterintuitive. These guys were brilliant to come up with this. They started at the hot end and went down to cool end down here. So they've created this here, and here's your colours matching up here as well, and they've colour-coded this. Here's your Arcturus, that's a red giant, that's in the sky at the moment. Here's your Betelgeuse, and Antares will be up there as well. These are red supergiants. And our sun, we'll be talking more about this shortly. So that just gives you a bit of a rundown of it. And so what is the point of all this? It tells you when you look at a star at what stage, and you're going to hear all this shortly, but I'm giving you a wee introduction. You actually get an idea from this graph at what stage a star is in its life. And as you'll see, what you immediately understand what's going on inside that star at the same time. That's what this diagram, you're going to learn tonight, the information they can learn from this diagram. Hugely powerful. So let's take a step back for a minute. It's introduction to astronomy. So, okay, how do they measure a star's brightness and temperature? Let's have a look. Okay, so measuring a star's brightness, it's called magnitude, how bright something is. And like most things in astronomy, everything's standardized. You can't just have some crazy, everyone's doing their own different thing. Everything is standardized, everything's calibrated, all their observations. Once again, it's logarithmic because there's a huge scale in brightness, as you saw off that graph. And so this is the magnitude scale here. In typical astronomy, they do everything a little bit funny. So the brighter something is, the more negative it is. So something with, say, our sun is about minus 26, 27 odd, and something really dim is positive 10. So it just goes the opposite direction that you would normally think. But hey, that's how it goes. Those figures there are all apparent brightness, which we'll talk about shortly. So to go about measuring it, once again, everything's calibrated, everything's standardized. They put a filter in front of your computer. They don't just gather the light in through the telescope and, oh, let's see how bright it is. No, they put a special filter on, and you can get all sorts of different standardized filters. Typically, they use what we call a V filter, and that V stands for visual, because, you know, light comes in a wide, huge range of wavelengths, and our eyes are sensitive just to a relatively narrow bit. But if you expand that out, you've got sort of blue end and red end, and you've got your yellow, sort of green, where our eyes are most sensitive at picking up. So they call it V for visual. And it's centered on about 550 nanometers, just these where they're centered on. And it's about 90 to 100 nanometers either side of that. So they let through the light only of a specific wavelength, so that helps to standardize it so you know what you're dealing with. Then your CCD detector at the other end of your telescope, that picks it up and that detects how bright something is and gives you a figure for how bright that particular star is. And even then, that is calibrated against already well-known stars and so on. So everything's standardized and calibrated. They get their magnitude. Now, what they're measuring is apparent magnitude. There's two magnitudes, brightness. Apparent, that's how bright it looks through your telescope from Earth. And then there's what we call absolute magnitude, which is actually how bright it actually is. And that's standardized too. That's at a set distance from the star, 10 parsecs, which is roughly about 33 light years away. That's, once again, everything is standardized. So they measure the apparent brightness by doing that. Now, just with that logarithmic scale, by the way, 0 to 5 to 10 going either way, it's designed whereby 5 magnitudes difference is a brightness factor of 100. So, say, for example, between something that was -5 and -10, that -10 object is 5 times brighter than, 100 times brighter. So 5 magnitude difference is a brightness factor of 100. You bring that down to 1 magnitude difference between, say, a 5 and a 6. It's a factor of about 2.512, roughly. Here is the concept here of absolute and apparent brightness. So obviously the thing to factor in is distance. That's going to, obviously, doesn't make sense, doesn't it? It's distance, the main thing that's going to separate your absolute or intrinsic brightness from your apparent brightness here. So once you know the distance of something, once again, it's a thing in astronomy they use at times called parsecs. Long story, we do a couple of talks on measuring distances in space, but needless to say, a parsec is about 3.26 light years. Just take that one, they just do that. And there's a very simple equation called the distance modulus, where absolute brightness is your one that you measured, your apparent brightness, times, and there's a logarithm equation there with your distance in there plus 5. So that's a very simple equation. If you know how bright something is through your telescope, you know the distance to it, which there are other ways, various ways you can do that, that's no problem. You know how bright, actually the intrinsic or absolute brightness of that star. So suddenly you've got the brightness factor, which is, you can quite happily put that on your Hertzsprung-Russell diagram. But just say you want to go one step further, because you think you're going to have some fun, and you want to put luminosity, the actual grunt, the power output of that star. once again, straightforward equation. Luminosity equals 4 pi, because you're looking at the whole star, not just how one slice of it's coming towards you. You're looking at the whole star, so you factor in there 4 pi. The distance squared, this time distance is in meters. You notice how things change with equations, so you just got to be very careful when you do your calculations that you're dealing in the right, times the apparent magnitude. So once again, if you know your apparent magnitude and your distance, you can work out the luminosity. That equation will give you the luminosity in watts, which is what joules per second, the actual figure. But as I mentioned earlier on, often you'll do it as a function of the luminosity of our sun. Whenever you see L as luminosity, whenever you see that little subscript there, that little circle with a dot in the middle, that refers to our sun. So you'll often see an L for luminosity with a little dot, and that means our sun's luminosity. Likewise, you might see a big capital R with that little symbol as a subscript. That means that's referring to the size, the radius of our sun. The same is magnitude. You'll see a big M with that little subscript. That you're referring to the absolute magnitude of our sun. So that's just something to throw in there. For the newbies here, if you see that little subscript, that's referring to the sun. So the luminosity of a star divided by the luminosity of our sun, and there's your equation there, 10 to the power of, with your once again, the magnitude, the absolute magnitude of the sun, minus the absolute magnitude of your star of interest, divided by 5, and you factor in, so it's 10 to the power of that equation. So once you've measured your star, you can work out so much from there. Okay, so that's how to measure how bright something is for your y-axis, whether you're interested in plotting brightness, absolute magnitude, or luminosity. How about your temperature? So how do you work out the temperature of a star? And it all comes down to spectroscopy. It's an instrument, a spectroscope that you put on your, see, instead of your field, you put your spectroscope on there, and it'll have a prism or some grating in there that splits light up, much like a rainbow. Of course, you can't do a talk with a spectroscopy without the Pink Floyd Dark Side of the Moon cover there. So, but my point being is the light goes through there, the prism, and the light splits up into its various wavelengths we're looking at here. So how does that tell you the temperature? Well, if you get a plot along here, the intensity of the light at various different wavelengths, and you spread it out across here, here's all your wavelengths of your light, and there's a distinct pattern. This is what they call black body radiation. In other words, a body, whatever it might be, that is pumping out energy, light, and all of the light it's pumping out is essentially light it's generating. In other words, you're not being soiled and mixed up with light being reflected off it and so on like that, because black absorbs things, doesn't reflect so well. So that's why they call it black body radiation. It's just a term. Now, what you can do is for various objects, and here they've got objects of different temperatures, and they've plotted these big curves here, and they've actually put the temperatures you can see just on the curves, like this way down curve here. It represents a black body of 2000 Kelvin, or let's call it a star now, 4000, 5000, and so on. And you'll notice the pattern there. As the temperature of an object, in this case a star, increases, the intensity of the overall light increases, because you can see the graphing up, but also the maximal wavelength gets shifted to the hotter, more energetic, shorter wavelengths. And you'll see here's your wavelengths here. But notice here, like let's take the extremes, like 2000, the peak wavelength is way down here in terms of low intensity, but the wavelengths here, but look at 5000. The overall intensity is really, really high, but notice the peak wavelength is much shorter than over here. Okay, you might say, yeah, I get that. What does that tell me about the temperature? Very simple equation. It's called Wien's law by an astronomer called Wien, and whereby your maximal wavelength, so that the figure, whatever this is, and you drop your line down there, you take that figure, equals B is a constant for the equation, Wien's constant, divided by the temperature. So you've already measured that with your spectroscope. There's your constant, that's a known, and there's your temperature. So you can work out the temperature of a star. So that's one way you can do it. You can also do it, confirm that with your spectroscope, because a spectroscope will often have, when you see these nice colours, spray colours, you'll see little dark lines running through them. And that represents different atoms in different states of excitation, and they're absorbing different energies. Each one's a fingerprint. The exact wavelength of a dark line where light's been absorbed is like a fingerprint that'll tell you the exact what element that is, what atom that is, and what energy state it's in, how many, whether it's lost electrons, whether it's in a neutral state, how many electrons it's lost. They get all that information. And these things are all well known here. So you have a look what your spectroscope shows, what it's peaking in, and you can see here that relates to its temperature as well. So if you see, for example, a particular atom in there that's clearly missing 5 or 6 electrons, you know, whoo, that surface is hot. If you see some lines that correspond to low wavelengths where you happen to know that there's the atoms are sitting there in a nice neutral state, there's even molecules sitting in a neutral state, it's not hot enough to pull them apart, you know you're dealing with a very cool surface. So you've got those two methods just through splitting the light up. And that's how they tell the temperature. So already, you guys can go out now and do your own Hertzsprung-Russell diagrams. Next month's homework. You get a spectroscope first, yeah. So I just put this in here. So there's a thing they classify, because we talked about colours and stuff as well, and how they classify stars. So it's called the Harvard Spectral Classification System. Here's the surface temperature, the ranges which they go from here, and here's the colours that they correspond to. Here's some very popular examples. And this is the classification here, O, B, A, F, G, K, M. And you might think to yourself, when I went to school, the alphabet went something like A, B, C, D, E, F, G. Well, certainly when I went to school, I thought, what are they up to these days? They did go A, B, C, D when they didn't understand stars so well. So they were looking at the hydrogen, the strength of hydrogen lines, and they classified them that way with A, B, C, D. And slowly, as the advancement, they started to understand stars better, in particular with the Hertzsprung-Russell diagram, they realized, whoa, we've been classifying or labeling stars wrongly. We should be doing it in a different way. But they kept the historic letters associated with them. There's a little mnemonic for that, oh, be a fine girl or guy, kiss me. So that's the little mnemonic that is commonly used for it. But there you go. So the classification is there, the Harvard classification. So that just puts it in context. Okay, so I put this equation in here to show you that luminosity, the power output, the temperature and the size of a star, those three parameters are all tied in together and form a relationship. And here's the equation here. You think, oh my God, this looks tricky. It's not. Luminosity, the power output, 4 times pi, you've seen that in equation before. Radius squared, it makes sense. The bigger a star is, the more luminous it's going to be. Just like pi is a constant, a sigma is a constant as well. It's the Stefan-Boltzmann constant. This, by the way, is called the Stefan-Boltzmann equation by two astronomers, Stefan and Boltzmann. Temperature to the power of 4. So that has 2 important implications. One is that stars of high luminosity are either really big, because they've got big radiuses, or they're really hot, or they're both. That's what that equation tells you. But it also tells you, after measuring a star's luminosity and its temperature, which you know how to do now, you can calculate the size, the radius of a star. Because you ever wondered, some people say, oh, the astronomers you're reading a book or on the internet, oh, a certain star, this is how big it is. And you think, how do they get out there and measure the size of a star? You can do your luminosity with your filter on your telescope. Your spectroscope will tell you the temperature. Use that very simple equation, and there you go. There's your radius, the size of the star. There you go. So that's important. So let's move on now. So that's a little bit of introduction. Let's move on to now to main sequence stars and what's that all about. And you probably saw the label here next to this big, wide, big, long band of stars here called the main sequence, which our sun's in the middle of. So what is that all about? And I think the good time now is just take a quiet step backwards and let's have a look at how stars evolve in one nice, simple diagram. Stars initially form, you get a big cloud of gas and dust, and They'll be in a nice state of equilibrium, and something will trigger it to start collapsing in onto itself, and you get these little knots, if you will, concentrations of gas and dust that form into individual stars, and you get a star cluster. Now, stars then are split into two main groups: low and medium mass stars and high mass stars. And it all comes down to how they come about. That it's all defined by how they end their lives. And it so happens that the low to medium mass stars are stars anything less, or 8 or less than about 8 solar masses. Here's your little symbol again, your little subscript. That tells you we're talking about the mass of the sun, so 1 solar mass. So anything less than that usually goes down this line here, which we're going to go through. And then greater than 8 solar masses are considered high mass stars. Stars spend 90% of their time in the state called the main sequence. By definition, main sequence stars are fusing hydrogen into helium. Hydrogen, remember, is just one little single proton, ramming them together to create helium nuclei, which have 2 protons and 2 neutrons. That's the subject of another talk. Then they swell up, these guys here swell out to red giants. Then their outer layers puff out into what we call planetary nebulae. You've probably seen these lovely pictures on the internet, on books, and the core becomes a white dwarf. We're going to be going through this in more detail. I'm just putting this up. I'm just taking a step back so we can just look at this and take it in one simple diagram, putting everything in context. The big mass stars greater than 8 solar masses go into red supergiants, and you'll see why they get so very large. They, at the end of their life, which we'll talk more about, explode as big supernova explosions. At the end of that, the core collapses, and if a star is between roughly 8 to 20 solar masses, the core will collapse down and find some resistance, and it ends up in what you call a neutron star, which you may well have heard about previously. Greater than 20 solar masses, as a rule of thumb, the core is under such gravitational forces, it just keeps collapsing right down to a single, what we call a singularity, tiny, infinitesimally small, and it's called a black hole. So that was the purpose of that diagram there, just to put it all into context for you. Okay, so our sun, as we talked about, our sun is in the main sequence. 90% of a star's lifetime is all in this nice stable state of hydro-equilibrium. That's it there. In 10% of their life, they come as an end stage as a red giant or red supergiant. To give you an idea how much they swell, our sun, that's 1 solar mass, will swell out to the size of Earth's orbit. You know, the sun to the Earth is 150 million kilometres. In other words, 300 each way. Our sun in the middle will swell out to there. That's what the estimates are, to become a red giant. Betelgeuse is already, obviously, a red supergiant. If you were to plonk that in the middle of our solar system, it would extend out to the orbit of Jupiter. Let me put that in perspective. My thumb says the sun. My little pinky is the Earth, 150 million kilometres. Jupiter is 5 times that out. So here's the sun, Earth. So let's go 2, 3, 4, 5. Jupiter's 5 astronomical unit out. So the sun's here. Jupiter's orbit's here. Put Betelgeuse here, it would go out to here, and of course the same distance out here as well. That's how big Betelgeuse is right now. It's a red supergiant. And as you saw, it wasn't the largest by far. Antares is significantly larger, but it just puts it in perspective. Now let's talk more about the main sequence stars, where they spend 90% of their life. And as we talked about right at the very beginning, these main sequence stars, under the huge temperatures and pressures, hydrogen, protons getting positively charged, they just overcome the repulsion, electrostatic forces, trying to repel them. They overcome that. They fuse together, form helium, huge amounts of energy is released, and that sort of pressure equals the gravity pressure. Hydrostatic equilibrium. Inward pressure of gravity is balanced by the outward pressure of nuclear fusion. And as I mentioned, that's just driven by huge temperatures and pressures, driven by gravity. Gravity is the driver of it all. So, when you look at that graph, why is the main sequence? It's so big, as you can see. You know, most of the stars, most of those little dots that are plotted there, sit all in that main sequence. And it is so long. Look at this, it almost takes up the whole graph, going in this diagonal path there from the top left down to the bottom right. And it's so wide. So why is that so? Well, you can explain it all. It is so big. Stars spend 90% of their life on the main sequence. That infers that 90% of the stars out there are all on the main sequence. It follows. The large variation, in other words, the length, how it's so long, because of course this is representing the huge temperatures and huge luminosities. That's what that's representing. Stars come in such a large variation in mass. Remember, mass creates gravity, and gravity is the main driver of temperature, of luminosity, also, which we'll talk about later on, lifespan as well. Not only are these bigger stars much brighter and more luminous and hotter, they also have short lifespans as well, because they're burning through everything ultra fast. To give you an idea of the range of masses of stars, they range anything from, one solar mass for our sun, from anything from little as 8% of the mass of our sun, 0.08 solar masses. And they can go quite happily up to 150. There have been some isolated cases. They think stars, one or two stars that have identified that could be a bit more than that, 200 or so. They're very rare and very unstable. The outer surfaces, they're so big, they can't control themselves. So you're talking, look at that large variation from 0.08 of a solar mass up to 150. So that naturally, it follows, there's a huge range in temperature and luminosity. And that's why the main sequence on this graph is so long and stretched out. So bigger mass, bigger inward force, bigger temperatures, faster rate of nuclear fusion, more energy, more brightness, more temperature. That's why the graph is very long. How about, and actually what I've put here, I just put this in here just to show you these stars are on the main sequence. Here's your classification. Remember that Harvard classification with the color and so on here. The more massive main sequence stars are brighter. They are positioned up here. That's why I put this up here. And these smaller and dimmer main sequence stars are positioned on the lower right, and they are down here. Okay. Once again, I want to take a step back again before we move forward again, just to explain a little concept. We talk about hydrogen fusion, two hydrogens coming together and to form helium. It's a bit more complicated than that, but it doesn't have to be. Needless to say, there are two main processes or mechanisms, if you will, at which hydrogen can be rammed together to form helium. One is called the proton-proton chain, because that's what hydrogen is. It's just one single proton, it's nuclei. So it's called the proton-proton chain. That has, once again, that's got the flow diagram of that could fill the whole slideshow. It's got various pathways, but there's main one pathway. But needless to say, the process called proton-proton chain, that dominates the fusion in the sun's core. But there's another one called the CNO cycle, and it involves carbon, nitrogen, and oxygen as the enzymes, if you will, catalysts that go into the whole physicochemical sequence. They go in there, they speed the reactions up, but they come out at the other end intact. So it's called the CNO cycle, carbon, nitrogen, oxygen cycle. That's another way, a chemico-physical process that you can get hydrogen to form into helium. That occurs at higher temperatures, but you'll see the graph here. So here's for any given temperature. Here's the energy output by the hydrogen fusion process. Here's your proton-proton chain here. But look at this CNO. It's far more efficient, isn't it? So for any given temperature, it pumps out so much more energy, And notice this is logarithmic, by the way, too. So it's pumping out the energy. The other thing you notice from this graph, though, you need a certain temperature for CNO to ignite, to kick in that process of hydrogen fusion. The core of our sun's about 15 million degrees. So it's mainly the proton-proton chain in our sun, with a little bit of a contribution, about 10% actually, from the CNO cycle. But you can see here, a bigger a star is going to get which means bigger temperatures at its core. The CNO cycle is going to be playing a bigger role in that. So not only have you got more mass, more inward force, faster nuclear fusion, you've got the CNO cycle in there as well going in. So you're really kicking up the, ramping it up. They're burning like crazy, those big massive stars. So that's the two main processes of hydrogen fusion. So just hold that thought. Okay, so here it is here. Here's the oh, okay, I've gone to a different function. Oh, it's quite nice, isn't it? I like the red dot. Here it is. So you'll see here, these big, hot, bright stars are up in the main sequence up here, the more massive ones, because they're bigger and massive, and they've got the CNO cycle going on. And that's pretty much what I've summed up here. Those big, large stars, they're on the upper left of the Hertzsprung-Russell diagram due to the higher mass, inward force, and the CNO fusion. So you can see the relevance of that past slide. You think, okay, I get that. So that explains why it's so long and wide. It also it explains why it's so big, because it's 90% of the stars. Hey, but why the width? Why isn't just a single line? Why has it got some width in there? And the reason for that is stars increase in luminosity on the main sequence. It's not just they sit there turning away, turning hydrogen to helium, and they are nice and stable in that hydrostatic equilibrium in terms of they're holding things together. They're not rapidly expanding and what have you, but they increase in luminosity. And why is that so? Hydrogen forms into helium. Helium is heavier. So all this is happening in the core. So the helium being heavier slowly sinks to the center of the core, and this just keeps building up and building up and building up. So slowly over time, the core of that star is just quietly, the center of it, starting at the center, is building up more and more helium. It's hot enough to burn hydrogen to helium, but not helium into anything further at this point in time. Just putting it in perspective, our sun's temperature, core temperature is 15 million degrees, quite sufficient to burn hydrogen to helium. To fuse helium, you need 100 million degrees. So you're a long way to go. So the helium is inert, it's nice and stable. It's not fusing or burning at this point in time. So it keeps building up, building up, and building up. As it's doing that, the amount of nuclear fusion obviously is going down because you've got less hydrogen to burn. So you've got less outward force. So the star starts, in particular, the core, just starts to contract down a bit. And what happens when something contracts and temperatures go up? Things start to burn a little bit faster and so on. And that nuclear fusion rate that starts going on because the core collapsing increases the luminosity of the star. And our sun is certainly more luminous now than it was, say, 3 or 4 billion years ago. It's significantly more luminous because the helium is building up in the core, less nuclear fusion going on, so the core starts collapsing because you've got less outward force, raising the pressure and temperature. The rate at which that nuclear fusion occurring is being ramped up, so the sun is getting brighter very slowly. So that's the main sequence. That's why it's so big, that's why it's so long, and that's why it's wide. And that totally explains what's going on with main sequence stars and our sun. So here we go. Here, there's our sun. That's where it all fits in here. We've talked about the main sequence. Let's now move on to red giants and red supergiants, where stars spend the last 10% of their lives. Here it is here. Okay, now we're talking now, we've moved on and we've now gone to the upper right-hand part of the Hertzsprung-Russell diagram where things are cool and they are very, very bright. So why is that so? Let's have a closer look. Okay, so let's move on from that. So we've worked out that slowly the helium is building up and nuclear fusion ramps up. So in a relatively sort of, as time moves on, you've used up all the hydrogen, the fusion. Any fusion that can occur, those conditions, has burnt up. And you've got an inert core full of helium ash, they often call it. It's just helium sitting there. The temperature's not up to 100 million degrees yet. Nuclear fusion has stopped because of that, so the star starts contracting inwards. Temperature and pressure starts rising, where that's heading, for hopefully to 100 million degrees, and helium will eventually kick in and start fusing. But before then, there's a period of time. And it's only a few thousand years, 10,000 years or so, which to us is a long time, but to a star, it's a blink of an eyelid. So it's a few thousand years where nuclear fusion, there's no nuclear fusion going on at all. It's just, the star is, the core of it's essentially dead. And the star starts contracting in and the pressure and temperature is rising. What happens then is the temperature starts rising enough to kick in, ignite a shell of hydrogen around the core. We're in here. So this is the inert helium. It's not hot enough for fusion, but you've got this hydrogen shell, this burning hydrogen here of nuclear fusion. That continues, that whole process continues. And this is where the star starts to swell up. You've got such a huge, as you can imagine, the surface area of the shell is significantly huge. Just simple mathematics tells you that there's your surface area of the core. The surface area of a shell is significantly larger, so that you've got more nuclear fusion, more energy, so the star starts to swell up. But there's a bit more than that. One is the large shell surface area. Here's your CNO fusion again. Those temperatures now, remember the temperatures are starting to rise higher and higher in that core. That's fueling that hydrogen shell, and that's one of the biggest factors. In fact, you've got CNO, you're really grunting up. The rate of nuclear fusion is quite intense in this hydrogen shell, and it's got a large surface area. And those are the two factors that start pushing the star out. The star doesn't change its mass, it's just changing its size. So it's becoming less dense. It's just really bloating and swelling up. Now, the next question is, with these red giants and red supergiants, see, that explains why they're getting bigger in size, but why are they getting red? And they're getting red because suddenly the surface area is so much bigger. You get the same sort of certain amount of energy going on in there, but suddenly your surface area that the energy's got spread over is just hugely, drastically increased, significantly. So that for any one region of a star, the surface temperature is much lower, so it turns red. You're getting down to 2.5. You can see here 2.5, 3,000 degrees, despite it being so large. But because it's so large, yeah, the actual per unit of temperature goes down, so it becomes a red color. Now, here's your equation again that I put in, that Stefan Boltzmann equation: luminosity, 4 pi, radius square, and temperature. So the temperature's dropped, yes, but the radius is hugely significantly increased, and that's why they are very bright. Size, remember what we said earlier on, that bright objects are either hot or the large or the both. These guys are very cool, but they're hugely large, and that's what's causing them to be really, really bright and luminous, and that puts them up in that corner there, the right-hand upper corner of the Hertzsprung-Russell diagram. Okay, so what happens from there is that slowly the temperatures and the pressures increase in that core, and you reach the magic figure of 100 million degrees, and suddenly helium can start ramming in to form oxygen and carbon. And the same process where you had a helium and then you had a hydrogen shell, you start getting a helium burning shell as well, as the carbon and oxygen build up, and you need much higher temperatures even again to fuse these guys. So they sit there as the inert, lifeless core, but you've got this shell, outer shell of hydrogen and helium burning. And so suddenly you've got two shells now going. So it's really puffing out and getting quite swollen, bloated, and red. Now, for stars that are greater than 8 solar masses, so those stars less than 8 solar masses, there was only enough mass to create enough inward force of gravity to fuse helium to carbon and oxygen, and that was it. There wasn't enough mass to drive it anything further than that. But stars bigger than 8 solar masses, they've got much more mass. They've got sufficient mass for sufficient inward gravity to start fusing carbon and oxygen together, which then creates, you've got your magnesium, neon, sulfur, silicon, and then through to iron. So you've got the whole series as the temperature just keeps ramping up in the core. And the same process starts occurring. So you've got, you slowly get, eventually you make iron, but you've got these outer shells, the silicon and the sulfur, magnesium, neon, carbon, oxygen, helium, and then out to your hydrogen of nuclear fusion going on. So instead of one shell pushing a star to a red giant, you've got multiple shells. They often call it like an onion, you know, the onion layers, how an onion's all designed. It's sort of, you've got these onion layers, if you will, of all this, each one nuclear shells of nuclear fusion, each one's hotter and hotter. So it's really blowing these things out. And that's why your Betelgeuse, you know, extends way out to the orbit of Jupiter, and why your Antares is larger than that. These guys are red supergiants for that reason. Suddenly then with these guys, and we're going to be talking about stellar remnants shortly, with those red giants, you're just left eventually with the core of hydrogen, carbon and oxygen. With these guys, you get to a core of iron. Up till now, nuclear fusion generates, it's called exothermic, it generates energy, and that's what drives the cell out, the swelling of the stars. Iron, you bring two irons together, try and fusion them together, that absorbs energy. It's endothermic, so it absorbs energy. So suddenly, any outward force stops instantly, and this is happening all in the way in the time frame of seconds now. You're dealing in seconds. Everything comes to a grinding halt. Not only does nuclear fusion stop, it actually starts absorbing. You need energy input. The whole thing just turns to custard. The whole star and the core just collapse in on themselves. You get a nuclear explosion with your supernova explosions, which we'll talk about shortly. And this is it right now. So that's stellar remnants. White dwarfs, because you probably saw this here. We've done our main sequence. We've done our giants and our supergiants, now white dwarfs over here. So they are reasonably, they're hot, but they're not very bright. So what's going on there? Let's go back to now our nice little evolution diagram. So these ones here, these red giants, nuclear fusion comes to a stop. You've got it, these things, there's still some outward forces, and we touched upon that with nuclear synthesis. There's a lot of pulsations going on, convection dragging material up and so on. And slowly these outer layers of it start getting pushed out. And over about sort of 10 to 30,000 years, it gets further and further pushed out, and you get these lovely planetary nebulae. But in the middle, you get the stellar remnant, the core, that oxygen carbon core. And it's very small. They're about, a white dwarf is about the size, got the mass of about sort of this half of the sun, and they're about the size of Earth. So they're relatively small compared with a star. Consider this volume-wise. Earth fits 1.3 million times into the sun, just to give you an idea, or diameter-wise, 110 times. So suddenly you've got something at the mass of sort of 0.5, 0.6, anything up to 1.4 solar masses in something the size of Earth. Very compact, so they're very, very hot. So they glow very brightly. There's the red supergiant we talked about. You get to iron, you try and fuse iron, and you get this results in a massive supernova explosion, and you form these neutron stars here, or a black hole for greater than 20 solar masses. We're going to talk a little bit more detail of those now. So here is your white dwarfs. As I mentioned, those outer layers shed, you've got this carbon, oxygen, it's hot, it's emitting. What's going on here? Here's the core here. Why is all this gas glowing or fluorescing? It's because of the intense ultraviolet light that's coming off this really relatively small but extremely hot object emitting ultraviolet light, and it fluoresces, bumps electrons off, and then the electrons come back again to the atoms, and the whole thing glows quite nicely. And typically they're about 0.6. They can go up to about 1.4 solar masses, then they become unstable. But yeah, on average, typically about 0.6 solar masses, diameter of the Earth. That's these white dwarfs here. And it's what it is, it's the core from the carbon and oxygen core that can't fuse. There's not enough mass to create enough inward gravity to do that. So I should go back. Let's just why I've got this graph up here, and here they sit here, because why are they really hot? Because the extremely hot ultraviolet light they're giving out, but they're also not very bright because they're very small. So they're low luminosity. Remember, luminosity is a function of size and temperature. So they've got some luminosity because they're hot, but they're relatively compared to a star, these guys are tiny. So they're not very luminous at all. So they sit down here. Now, as we mentioned here, ion fusion generates a supernova explosion, and you get a very hot, small neutron star. The neutron star sits way down here. So these neutron stars are the most compact, dense objects known, not counting the whole thing of black holes, we won't go there. These things are anywhere between 1.4 up to about 2 solar masses, the diameter of a town or a city, 10 to 20 kilometers across. If you've got a teaspoon off it, it would just fall straight through the Earth. Now that's how heavy and dense. These are the most densest objects known in the universe, these neutron stars. So they are extremely, extremely hot, but because you're talking 10 to 20 kilometers across next to nothing, they sit way down here. They're not very luminous at all. So they sit way, way, way down here. So that's your stellar remnants. Now there's a few, the other thing you've probably noticed here, let's look at gaps and variations. You've probably noticed there's some gaps in here, like, because everything's formed in little groups. Why the gaps in there? That one there, this gap here, by the way, is called the Hertzsprung gap in here. And it's because stars, their lifetimes are dominated by these phases where nuclear fusion is occurring. The transition phases between one phase or stage to the next, very, very short. Just you took a few thousand years, as we spoke about. For example, the main sequence stars before that shell starts forming. You're talking a few thousand years, just a bat of an eyelid. So very, very short. So you very rarely see them there. And that is why that you have these little gaps here and they actually form groups. Now, there's a couple of variations or spin-offs, if you will, of having the Hertzsprung-Russell diagram. You can see the point in it. You can predict where a star is going to travel, and it's over the billions and billions of years, how it's going to change in luminosity and temperature. You can look at a star and see where it fits on that graph with its luminosity and temperature. That tells you whereabouts in its life cycle it is. But you can tell other stuff from this as well, other little spin-offs. One of them is the evolutionary tracks. That's pretty much what I was implying then. So you can actually start drawing tracks here for a given mass of a star on its main sequence. You can actually work out the physics of it and with your observations and see if they match up. And you see these little evolutionary tracks. And from there, you can, given a star of any given mass, you can predict its future evolution and properties. Given a star with known luminosity and temperature, which you measure, you can determine where it is in its lifespan. Very, very useful. Everything has implications. There's another one here called the color magnitude diagram of star clusters. So if stars come in clusters, they can be an open cluster here, typically very young. That big cloud we talked about, cloud of gas and dust that's started collapsing into itself, and these little knots of stars will form. Each of those forms what we call an open star cluster. So all those stars are all brothers and sisters, siblings, if you will, and they're all born at the same time, from the same gas cloud, so roughly the same composition, and of course they're going to be the same distance from us, aren't they, roughly? Globular clusters are very old, a group of old stars, very densely packed in. There's all sorts of theories how they probably originated perhaps from galaxy mergers and so on. That's a whole different talk on that, but needless to say, there's these star clusters. And when you draw your HR diagram from here, you assume that all stars are roughly the same distance because they're all formed from the same sort of parent, if you will, cloud of gas and dust, large molecular cloud. The other thing is their magnitude. You can, instead of actually having to get their actual temperature, with your magnitude, say your V filter, get all your recordings for your V filter, but maybe do a B filter as well. It's sort of the bluer end of the visual spectrum. And the difference between the two indicates the color. They call it the color index. And that's a good representation of your temperature. Now, the other thing I'll mention in here, because they're all the same distance, you're not interested anymore in their absolute magnitude. You don't have to worry about that. You just go by the apparent magnitude because you've taken care of the distance factor that alters it. So you can just assume they are. So All you have to do is get your telescope, use your V filter, use something like a B filter as well, plot your V filter here, and that's your apparent magnitude. That will suffice. Your B minus V filter is the color index, and that represents the temperatures as well, the colors, which correspond to temperatures. And there you go, you can do it just with one set of observations. You can form an HR diagram. It's called a color magnitude diagram. And the implications here is that you can estimate loads of things, actually. Two big ones, though, is the age of the cluster. You know, when they say, oh, this cluster here is so many millions of years old. How do you know that? Remember the main sequence. We talked about the main sequence goes up through here. And we also spoke about the higher mass a star is, the faster the rate of nuclear fusion, the more energy it's pumping out to the CNO cycle as well, shorter life. So they can work out, and once again it matches observation, they can correlate the age of a star, how long it's going to live according to its mass. So some of these big stars, you know, our sun's going to live about 12, total lifespan about 12 billion years. They know, for example, that a star of, say, 100 solar masses only going to live for a few million years, fraction of the time. They burn through their fuel so much quicker. So that's very easy to know. There's nice charts that will tell you exactly. So suddenly the main sequence should go up here, but suddenly it cuts off here. That's called the main sequence turn-off point. And you can take that from exactly that point, and that tells you all the stars from up here have all been burnt out. These stars here are still living. And once again, you can work out from the lifespan, you can very quickly work out what that mass is, the mass of a star. You know its luminosity, its brightness, you know its temperature. You can work out from there its mass and so on, and you can very easily work out exactly what time that is. So all the stars here, and that's how it's called the main sequence turn-off, and that's how you tell the age of a cluster. You can tell the distance to the cluster. They get once again, an already standardized and calibrated, well-known color magnitude diagram. They overlay it here. They've what they call main sequence fitting. They compare the brightness and they shift it up and say it might be sitting out here. And the difference between the two is the difference in the distance to the cluster. You know, the distance modulus equation. So this is obviously your parent recording here and your absolute here with your main sequence fitting. So we can do a whole talk on that. Okay, so let's wrap up. Summary and conclusion. So the Hertzsprung-Russell diagram, it plots the luminosity as a logarithmic scale here, or its brightness, the temperature or the color across here, hot at this end, going over to cool at this end. That is the periodic table of astronomy. So just like the periodic table is to chemistry, the HR diagram is similar to astronomy. And it's extremely a powerful tool, arguably the most powerful tool astronomers have to identify and predict different stages of stellar evolution. And that's the Hertzsprung-Russell diagram, stars and stellar evolution explained. Thank you. Thank you. Any questions as I finish my gin?
Just around Earth's risk of a supernova. What's the most immediate suspect?
Some distance right now, I couldn't tell you, oh, it's this star here.